matrix is a diagonal matrix of size 3 by 3. So therefore, the 0 vector has to be in D33, right? So this first one checks out. I'm going to use a red marker to say that this checks out. Check. 2. What's the next one? Well, if you have two diagonal matrices, right? When you add them together, you end up with a diagonal matrix. So that. Let's say I have U equal, I make a diagonal matrix here. I have A, 0, 0, 0, B, 0, 0, 0, C, right? Where A, B, and C could be any real numbers. And I have V, I can have that be D, 0, 0, 0, E, 0, 0, 0, F, right? Where D, E, and F can be any real number, right? Notice that U and V are both diagonal matrices, right? Because that's what it says. If U and V are in W, so they must mean that U and V are both diagonal matrices. If U and V are both diagonal matrices, then if I add them together, do I end up with a diagonal matrix? So let's do that. So U plus V is equal to A plus B, 0, 0, 0, B plus E, 0, 0, 0, C plus F. And lo and behold, this is a diagonal matrix. So I can say U plus V is in W. In D33. Okay. So if I have U and V are in D33, diagonal matrices of size 3 by 3, then U plus V is also in D33, diagonal matrices of size 3 by 3. And the last property is 3. When I do scalar multiplication, do I end up with a diagonal matrix of size 3 by 3? If U is a diagonal matrix of size 3 by 3. Look at that. 3. Okay. Suppose I have K times U, and I just like it A, 0, 0, 0, B, 0, 0, 0, C. Okay, let's just see by U here. Okay, K times U. K is my scalar, okay? I'm not using C, I'm using K. Big whoop, okay? U is a diagonal matrix of size 3 by 3. Okay. What happens when I do scalar multiplication? If I'm assuming standard scalar multiplication, I get Ka, 0, 0, 0, Kb, 0, 0, 0, Kc. This is also a diagonal matrix of size 3 by 3. So thus, I can say that K times U or C times U is in D33. That means that D33 is a subspace of M33, matrices of size 3 by 3. Okay. So there we go. 2 more and we're done. All right, 2 more, we're done. Okay. Which what do we want to do? Oh, yes, we'll just do the 3 and 4. I'm gonna put this down here. Let B equal M to 2. So we're staying with matrices. So matrices of size 2 by 2. And W is the set. It's a set of all invertible matrices of size 2 by 2. So that V equal M22, so matrices of size 2 by 2. W is a set of all invertible matrices of size 2 by 2. Okay. And I want to know, is W a subspace? What do you guys think? You should automatically say no, absolutely not. What's the problem here? The problem, if you've been looking at this, is that what in the world is a zero vector? What's the zero vector for M22? Okay, what's the zero vector in M22? Oh, I forgot to check all my other guys, right? Check. Going back, you get a check. You get a check. All right, there we go. Now everything's complete. What's the zero vector in M22? Well, it's going to be zeros in a 2 by 2 matrix, zero vector in M22. What's the problem? What's the problem that you face here with this one? Well, what is W? W is the set of all invertible matrices of size 2 by 2, right? We need to make sure that the zero vector is in W, but is the zero vector invertible? And the answer is no. The zero vector is not invertible, right? Its determinant is 0. So I have to say that the zero vector is not invertible. All right, let's make this one actually a little bit more interesting. Let's say W is the set of all non-invertible. That way it makes it a little bit more fun. Okay. Non-invertible means that this determinant is equal to 0, right? I mean, you can't flip it. So W is a set of all non-invertible matrices of size 2 by 2. So I'm just going to change the problem altogether. That way the zero vector is in there. So the zero vector of B is 0, 0, 0, 0, right? The zero. So therefore, this is a non-invertible matrix, and so this matrix will be in the set W. So I'm going to say the zero vector 0, 0, 0 is non-invertible. I just changed the problem. Sorry about that. So therefore, zero vector is in W. Okay. Now, if I kept it as invertible, I could have just stopped there and said, okay, the zero vector is not in W, and so it's not a subspace. But now I've just changed the problem. All right. So I can say check. Is U plus V in W? If I have a non-invertible matrix and I add it to another non-invertible matrix, will I get a non-invertible matrix? So if I have a matrix that has no inverse and add it to a matrix that has no inverse, can I get a matrix that has no inverse back, or can I get a matrix that does have an inverse? Is it possible for me to get a matrix that has an inverse when I add two matrices that don't have inverses together? Right? So two matrices, no inverse, add them together. Is it possible for me to get an inverse? If it's possible for me to get an inverse from that matrix, then that means that that sum is not in W. And the answer to that is yes. That's why I changed it. That's why I changed the answer. So let's look at it. So if I look at property number 2, U plus V. So suppose U is equal to, I keep it simple, 1, 0, 0, 0. V is equal to 0, 0, 0, 1. Do you see it? Does this matrix have an inverse? The answer is no. Does this matrix have an inverse? The answer is no. U and V are in W. and V have no inverses. They're non-invertible. So U and V are in W, right? But what happens when I add them together? One, zero, zero, one. Does this have an inverse? Yes, it does, right? This is the identity. It has an inverse, which is itself. Okay? So this has an inverse. U plus V has an inverse. It is invertible. Thus, U plus V is not necessarily in W. So that means that it's not a subspace. I can stop there. Therefore, W is not a subspace of V. Okay. So we've just shown it there, right? So I made it a little bit more interesting for you guys. Almost second to last problem of the semester. And finally, number 4, and we will be done. Number 4 in the PowerPoint. Let V equal, here have R cubed, and W is equal to all points, or all vectors, x, y, 2x minus 3y, where x and y are real numbers. So V is our vector space, and W is going to be the collection of vectors or points. It doesn't really matter how you want to think about it. Where we have essentially x could be any real number, y could be any real number, but z depends on x and y with the relationship of 2x minus 3y. Okay? And I want to know, is W a subspace of V? Okay. Is W a subspace of V? Let's go through the properties here. Is the zero vector in W? The zero vector in W. Well, what's the zero vector for R cubed? We talked about this one before, right? The zero vector R cubed is going to be 0, 0, 0. I'm going to write it in the vector form just because I like to see it that way. Instead of a point, I think 0, 0, 0. Now, is 0, 0, 0 in W? 0, 0, 0 in W. Now remember the form of W, right? X can be any real number, Y can be any real number, and Z depends on whatever X and Y are. And guess what? The zero vector is in W, right? All thing we have to do is pick X and Y to be equal to 0, right? Then what do we have here? We have the zero vector is equal to X, Y, 2 times 0 minus 3 times 0. 2 times 0 minus 3 times 0, by the way, is 0, right? So the zero vector is in W, because I can essentially write it in this form. I have 0, 0, 2 times 0 minus 3 times 0, right? 2 times X minus 3 times Y, same thing. So that means that the zero vector is in W. Check. What about 2? Second rule, U plus V. It's U plus V in W. It's U plus V in W. Now remember, if U is in W and V is in W, is U plus V in W is what I'm asking. if U is in W and V is in W, is U plus B in W? So let me write it this way. So I'm going to write U, and I'm going to write it vertically, and I'll say it has A, B, and then it's going to be 2A minus 3B. Okay, that'd be U, where A and B are just my X and Y. Okay, and V, I'm going to write that as CD, 2C minus 3D, where C and D are my X and Y. Okay, now notice that U and V are both in W. They have that same form, the same form that I have for all my points or all my vectors in W, is that X and Y can be anything, but then Z has to depend on whatever I pick for X and Y. So A and B and C and D could be anything, but Z is going to depend on whatever I pick for A and B or C and D. Okay. What happens when I add them together? Okay, let's do that. I get A plus C, right? B plus D. And if I add these together, right, I get the 2A plus 2C. So I can write this as 2A plus C. Okay, I can write like that. And then I have minus 3B minus 3D. So I can really write that as minus 3 times B plus D. That's the same thing, right? So now look at this. Do I have that same form that W is supposed to have? So my X is going to be A plus C, right? My Y is going to be B plus D. And then my Z is going to depend on whatever my X and my Y are. So it's going to be 2 times X, which is 2 times A plus C, minus 3 times Y, which is going to be minus 3 times B plus D. So that means that U plus B, no matter what A, B, C, and D are, I still get that the sum U plus B has to be in W as well. So U plus B is in W. So I can check that one too. Check. Finally, last one. Last one. We should savor the moment for a second here. Oh my. Last problem, last part of a problem for a semester. Okay. It's C times U in W. Okay. Well, let's use K instead. So I'll use K. I'll say K times U. K times U. So I'll say K times AB 2A minus 3B. Okay. Now when I multiply this through, I get KA, right? This becomes KB. This becomes 2 times KA, right? And this becomes minus 3 times KB. Now, do you see it again, right? So this is K times U, or C times U. It doesn't matter what you want to call it. It's a scalar times my vector. So X is Ka, Y is Kb. So I have 2 times X minus 3 times Y, which is exactly what I want to see here. 2 times Ka minus 3 times Kb. Same form that I have over here for W. So that means that K times U is also in W. So thus, W is a subspace of V. Now, since I know that this is a subspace of V, we know that V is in R cubed, right? We know that V is equal to R cubed, I'm sorry. So that means that this subspace must either be a point, a line, a plane, or all of R3, right? Now, what is this going to be? What is this subspace going to be? And it's going to be, I know I'm killing the suspense here a little bit, but it's going to be a plane, right? It's going to be a plane. Let's write it in vector form so you guys can see this. This is not the way we usually write it, but I'm going to write it the way they have it. So essentially I have X, Y, and Z. Okay, that's what we have here. Now x and y can be anything they want to be. So I'm going to say that x is equal to s, right? Well, let me do it this way first. Let me erase that. X, y, and z. Okay. Now x and y can be anything they want to be. So let's say x is equal to s, and y is equal to t. Z is going to be equal to 2s minus 3t. Okay. So this is the parametric form. And then if I write it in vector form, I have this x, y, z equals, we have one for s, we have one for t, and then we have one for the point, right? Okay. All right, so the vector for s is going to be, what's that, 1, 0, 2, I believe. The vector for t is going to be 0, 1, negative 3. And the point that it goes through, that this plane goes through, right, because we have two parameters and two direction vectors, so we know that it's going to be a plane. And the point that this plane goes through is 0, 0, 0, the origin, which is what we want to see, because 0 has to be in there, the origin. So we know that this is a plane. In R3, containing the origin. Containing the origin. Okay. All right, which is what we would expect to see. A plane is one of the subspaces of R3, one of the standard subspaces of R3. All right, so we are done with linear algebra. I hope you guys are well, and I hope you guys are doing wonderfully wherever you are. I know right now I'm a little bit frustrated with all the stuff going on, but I'm in the future. I'm in the past, and you guys will be in the future. I think I said it the opposite way last time. So maybe